Hello, my name is Qingfeng Wang from the University of Maryland, College Park. Today, I am going to talk about how to optimize fermionic simulation circuits. This talk consists of two major parts. First, I'm going to introduce standard approach to construct the quantum circuit. After that, I will introduce specific techniques I use to simplify quantum circuits. Here, we take a quantum chemistry simulation, for example. First, throughout this talk, we use the VQE algorithm to simulate molecules. In short, VQE is a hybrid optimizer that uses the quantum computer to deal with the most complex part, that is, to evolve an initial state with a unitary operator U. Then, the classical optimizer will retrieve the useful information to iteratively optimize and obtain a better energy estimate. The quantum computer uses the UCC answers as its evolution operator, which is simply the exponential of excitation operators minus its complex conjugate. Then, we use the first-order trotterization to break down the exponential of summations to the product of exponentials. After that, we need one more step of transforming fermionic operators to qubit operators. One of the well-known transformations is the Jordan-Wegener transformation, and it can be straightforwardly shown that, with Jordan-Wegener transformation, polystrons in qubit space follow the same fermionic anti-commutation rules. Without that, we can implement the trotterized excitation operators. One example I will show in the next slide. Suppose you have a U with a polystron that is the tensor product of four polymatrices. The corresponding circuit is shown in the middle. M are the necessary basis change for polymatrices. For example, M equals to R Hartman gate if the polymatrix is sigma x. Making use of this template, we can simulate an entire UCC answers on a quantum computer. The question is, how much resource it costs? In the current noisy intermediate scale quantum device, the cost is the number of 2 qubit gates. Here is a plot that shows how many number of 2 qubit gates you need in order to reach the chemical accuracy. We took a water molecule with STO3G basis as an example. The vertical axis is the energy difference between VQE energy and the exact full CI energy. As can be seen, it takes thousands of 2 qubit gates to reach chemical accuracy. Our goal today is to use a suite of circuit optimization techniques to significantly reduce the number of 2 qubit gates. Expanding one double excitation term using the Jordan-Wegener transformation results in product of 8 subterms. The unoptimized circuit implementation results in 48 signal gates. If we optimize the circuit as shown in the reference, the number of signal gates can be reduced to 19. We can further optimize by cleverly arranging the trotter subterms. The trotter error bound remains the same under the rearrangement. For instance, we could order the subterms according to order 1 versus order 2. If we implement a circuit with order 2 compared to order 1 with 19 signal gates, the optimized circuit requires only 13 signal gates. Another technique we can consider is to relabel fermionic indices. The reason why we do this because as long as we keep the anti-commutation relation, the fermions do not care which labels we give them. In this particular example, the UCC answers of A3 dagger A0 after the Jordan-Wegener transformation will result in 12 signal gates. If we relabel 3 as 1, the required number of signal gates reduces from 12 to 4. The next technique is taking advantage of bosonic excitation. In the restricted Hartree-Fock ground state, electrons are paired in occupied molecular orbitals. If a double excitation term excites paired electrons into the same virtual molecular orbital, we refer to this as a bosonic excitation. Circuits for bosonic excitations are much simpler because we only need 2 qubits to represent the process instead of 4, since the electrons always move in pair. Such a construction shows here requiring only 2 qubit gates, as shown on bottom right. The last technique explored is different fermion to qubit transformations. We all know the asymptotic behavior of these famous transformations. However, in the near-term VQE, only a small fraction of excitation terms are ever considered. It is likely we are never in asymptotic region. So, heuristic results are just fine. Therefore, what we need is a choice of transformation that works the best in practice. A generalized transformation looks like on equation 1. This expression requires applying sigma x on qubit indices defined in the set U and sigma z on qubit indices defined in the set P and R. The elements of this set can be obtained by constructing an invertible binary matrix beta shown on equation 2. Each beta matrix, of which there are almost 2 to the n squared of them, corresponds to a new transformation. To create this convenient set of indices, we simply fold the gray box. For example, the elements of the remainder set Rj are the column indices with non-zero entries in row j of the matrix pi multiplied beta inverse, where pi is defined on equation 3 and beta is defined in equation 2. Notice that the Jordan-Wigner transformation is a special case of beta being an identity matrix. To take advantage of these generalized transformations, we devised a workflow here. Essentially, we iterate over different choices of transformations and compute the cost of the optimized quantum circuits for every transformations we consider. The transformation that results in the minimum cost, found by a heuristic optimizer, is chosen to be our go-to transformation for use. Here's the result of the optimization. Left 3 curves show the results after circuit optimization with different transformations labeled at the top of each curve. We can see that with the circuit optimization, an order of magnitude of savings in the number of 2 qubit gates result. The improvement offered by the generalized transformations is input-dependent, as can be clearly seen in the table to the right, sometimes nearing almost 20%. Further investigations that better explore the super-exponentially large search space of the beta matrix will likely widen the margin of improvement. Now, I would normally wrap up and talk here, but I decided to tease some of our latest results. So far, we have only discussed ways to decrease the resource requirement by means of circuit optimization. However, in the grand scheme of quantum simulations, it is important to notice that we have target accuracies. Indeed, what we want to achieve is accurate simulations with least amount of resources. If we can achieve better accuracy with the same amount of resources, this in turn means that we can obtain the same quality simulation with smaller amount of resources. With that in mind, we introduced the HMP2 method. Without going into details, we can rewrite the UCC answers approach as a first-order perturbative method. Then, naturally, we may consider the second-order perturbations. This is called HMP2 method. This HMP2 method converges energy much faster than a standard VQE algorithm without increasing the size of the circuit. Using the HMP2 method, the green line is a state-of-the-art that combines all the circuit optimization techniques discussed in this talk. This plot shows that we can reduce the resource requirement significantly. We expect this method will help a quantum computer to simulate larger and larger molecules with a minimum resource requirement. With that, I would like to thank my collaborators and the funding agencies. Thanks for your attention.